Hi everyone. Today we're going to continue with our proof methods. So we left off with our proof by cases before we left for spring break. And then we took a quick detour to review our differential equations, and now we're back on to our proof methods. So today we are going to look at section 7.09, proof of biconditional statements. So a biconditional statement is just the if and only if statements. So we have this theorem that we're going to start with, which is going to drive everything that we're doing with these proof methods. So the theorem is that P if and only if Q is logically equivalent to, sometimes you might see this abbreviation or you might see 3 lines, just means logical equivalence, is logically equivalent to P implies Q and Q implies P. So if P then Q and if Q then P. So we're going to quickly do a proof of this theorem, and then once we've proven that, we'll be able to use this idea to prove biconditional statements, or if and only if statements. So the proof of this, we're going to go back to our truth tables. So this will be a good review of truth tables. So again, we want to start with alphabetical order of our statements here. So we have P and Q. So we're just going to have P here, Q here. And then we're only going to need 4 rows. Since we have 2 statements, we have 2 squared. So that'll be only 4 rows here. And then we're going to start with P if and only if Q. Then P if P then Q, if Q then P, P, and then lastly our AND statement. So P implies Q and Q implies P. Alright, so again, to start this off, we have our true, true, false, false. So half of P is true, half of P is false. And then Q alternates here, so true, false, true, false. And now we have if and only if. So the if and only if statement, just as a refresher, is only true if both statements have the same truthhood. So for the first one here, both P and Q are true, so this would be true. The next two, we have true, false, and then false, true. So those do not have the same truthhood, so these both would be false. And then the last one, we have false, false, so those have the same truthhood, so this is lastly true. For implication here, if-then statements, again as a refresher, that's a good way to just remember the only time that an if-then statement is false is if you have true implies false. So here, if we have true implies true, that's true. True implies false, well, that's where the only time we're false. And then if false implies anything, then that is true. For the Q implies P, we need to be careful here because direction matters. So especially in an if-then statement. So here we're starting with true, and so we have true implies true, so that is true. We have false implies true, that is true. We have true implies false, that's the only time an if-then statement is false. And then lastly we have false, false, so that is true. So now we need to AND these two columns together. And once we do that, again, an AND statement is only true if both statements are true. So we have true, true, which is true. False, true is false. True, false is false. And then lastly, true, true is true. So in order to prove logical equivalence, we just have to have matching columns. So in this case, we do have matching columns. So if we look at this column here and this column here, which are the statements that we are trying to show are logically equivalent, we have true, false, false, true. So we have just proved this theorem. So now we're going to use this theorem in action. So let's go ahead and prove a biconditional statement. So suppose a is an integer. A is even if and only if, so again this abbreviation for if and only if, IFF, a squared plus 3 is odd. So this is a biconditional statement. So in order to prove this, I'm essentially going to have to do this sort of method that we've indicated above, where I'm going to have to prove P implies Q and Q implies P. So I'm going to have to prove two if-then statements when I'm trying to show a biconditional statement. So in order to do that, we need to figure out what exactly are our if-then statements going to be. So let's just start with the forwards claim. So first we have proof of this. We will prove two statements. So our forwards claim is our P implies Q. So here we can say that this is essentially if A is even is our P statement, and then A squared plus 3 is odd, that is our Q statement. Let's just go ahead and label these. Then we can prove this biconditionally. So to start with our forwards claim, we have if A is even, then A squared plus 3 is odd. So I need to prove this if-then statement. And so this appears to be just a direct proof because my if part here is just a statement about the parity of A, and my then part is an expression that I'm trying to prove is a certain parity. So this fits my description of a direct proof, so let's just go ahead and prove this directly. So we need to assume the if part here. So assume A is even. So by definition of even, there exists a j that's an integer such that a equals 2j. So let's consider the statements below. So let's have a squared plus 3 is equal to 2j quantity squared plus 3. If we simplify here, we get 4j squared plus 3. And now I want to go back and I want to see, what am I trying to prove? I'm trying to show that a squared plus 3 is odd. So I need to get this into the form of 2m plus 1. So I see that I have this 3 here, and so I need to have this somehow to be a 1. So the trick that we learned is to just break up 3 into 2 plus 1. So here, that's what I'm going to do. So I have 4j squared plus 2 plus 1. And now I can factor out a 2 from these first two terms. So 2j squared plus 1 quantity plus 1. And so now I can have my 2m plus 1. So since 2j squared plus 1 has neither fractions nor decimals, there exists an m that's an integer such that a squared plus 3 equals 2m plus 1 by our definition of odd. A squared plus 3 is odd. I'm going to leave this as an open box because I have not proven my overall theorem, but this is one subproof inside a longer proof. So I'm just saying that yes, I have proven something, but that is not my final statement. So that was our forward claim. So now we need to do the backwards claim. I'm just kind of putting a backwards arrow here. And so the backwards claim would be Q implies P. So our Q was if a squared plus 3 is odd. So that's what we're going to start off with. So if a squared plus 3 is odd, then a is even. So looking at this here, I have an expression in my if statement. And this doesn't really help me all that much because I don't know anything about A. I'm trying to prove that A is even, but I can't assume anything about A. I certainly can't assume that it's even because then I would be assuming what I want to prove. So here, since I have an expression in my if statement, that makes me want to do the contrapositive. Before I even do that, well, the contrapositive would be, let's just write that down. Well, let's just say, because if it's not even true, then I might not want to even prove it. So the contrapositive would be, if a is odd, then a squared plus 3 is even. So let's just do a quick test for that. So let's pick an odd number. Let's just do 1. So if I have 1 squared plus 3, well, that would be 1 plus 3 gives me 4. So that works. If a is odd, then a squared plus 3 is even. Okay, so that seems to work. So let's just go ahead and prove this by using the contrapositive. So again, I'm doing so because I have an expression in the if statement. So I want to flip my if and then statement and negate them. So let's write, we'll prove the contrapositive, which is if a is odd, then a squared plus 3 is even. So, proof of contrapositive. So now we can assume a is odd. By definition of odd, there exists a j that's an integer, such that a equals 2j plus 1. So now we're trying to prove that a squared plus 3 is even, so we can start out with a squared plus 3 is equal to 2j plus 1 quantity squared plus 3. And if we expand that, we get 4j squared plus 4j plus 1 plus 3. Now if we simplify, we get 4j squared plus 4j plus 4. simplify. And now we can factor out our 2, so we're left with 2j squared plus 2j plus 2. And now we can say that this is 2m, so m equals 2j squared plus 2j plus 2. Sub that. So here we have, again, just finalizing this contrapositive proof. Since 2j squared plus 2j plus 2 has neither fractions nor decimals, there exists an m that's an integer such that a squared plus 3 equals 2m. By definition of even, a squared plus 3 is even. So this was the proof of our contrapositive, which was a subproof of our subproof. So we can say, having proved the contrapositive, we may conclude the original statement, which is if a squared plus 3 is odd, then a is even. So that's the end proof of our backwards claim. So again, this is an open square because it's not the proof of our totally original statement. The suppose a is an integer, a is even if and only if a squared plus 3 is odd. But we have gotten ourselves one step closer. We've proven the forward claim. We just finished the proof of the backwards claim. So now we just need a concluding statement for the two forward and backwards claim. So we can say, having proven the claim in both directions, we may conclude a is even if and only if a squared plus 3 is odd. So our final filled in box here, QED, we are done. So the trick for this is, for any if and only if statement, a biconditional statement, you have to prove the forward and backwards claim. In those forward and backwards claim, you might have to use another proof method to prove that if-then statement. So it won't always be direct like the forwards claim. It might be a contrapositive, or it might be a cases situation, or any of the other proof methods that we have discussed. So for your classwork for tomorrow, please make sure you are reviewing your notes. The proof for tomorrow is a substantial proof, and you need to make sure that you are looking at your notes carefully. All right, have a great rest of your day, everyone.